Okay, Assalamualaikum and good morning everyone. Thank you for joining us today. Okay, so this is a photonic lecture series organized by IEEE Photonic Society Malaysia. Okay, so before we start our talk, I would like to show you, to share with you a bit about IEEE Photonic Society. So let me play the video. You see the video? Okay. Okay. Right, so there's a little bit about IEEE Photonic Society Malaysia. If you are interested to know more about, we call it IPS in short, IEEE Photonic Society, IPS, you can email us. Okay, and actually we are conducting many activities, not only lecture like this, we also involved in community related STEM activities. We go to school to conduct activities that related to science. Right, so actually if you join, there are many benefits that if you join the society. Right, if you want to know more, you can search in our website. Right, so before we start our talk today, let me introduce our speaker. So firstly, thank you very much, Dr. Nadiah, for agreeing for the agree to give the talk today. The title of the talk by Dr. Nadiah is specifically pulse fiber lasers with the help of nanomaterials. Hold on. Sorry. Okay, so before we start our talk, let me introduce Dr. Nadiah. Dr. Nadiah Husseini received her Bachelor Engineering Electrical and Electronics Engineering from Universiti, USA in 2012. And then upon graduation, she was hired as radio frequency engineer by DG Telecommunications in Jan Berhad. In 2013, she was awarded with Erasmus Mundus Mobility Scholarship, where she did her research attachment with the Communications Lab of Northumbria University, Newcastle, UK for 10 months. And then within the same year, she received the Young Academic Trainee Fellowship under Universiti Putra, Malaysia, to pursue her PhD in Photonics Engineering. And then she completed her PhD study in random fiber lasers in the year 2017 and is currently extending her research to ultra-fast fiber lasers. She teaches physics at the Center of Foundation for Agricultural Science in UPM. And from time to time, she enjoys doing physics demo with her students. And Nadiah is currently affiliated with HPE Young Professionals Malaysia and is leading the Optical Society student chapter in UPM. All right, without further ado, I would like to pass the session to Dr. Nadiah. Okay, pass to you, Nadiah. Maybe you can share your slide.
Okay, can you guys hear me? Okay, tak? Because I'm using my hotspot.
Can.
Alright. Okay, so Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to everyone that is joining this session. I am Dr. Nadiah Husseini. You can just call me Nad. So I'm going to share with you about passively pulsed fiber lasers with the help of nanomaterials. But before that, I would like to tell you a little bit about my research group. I am from WIPNET, which stands for Wireless and Photonics Network. It is a research center of excellence located at the Faculty of Engineering UPM. And our members are expertise in sensors technology, electronics, photonics engineering, materials engineering, signal processing, wireless communication and networks. And currently we are also pursuing IoT. So our members are, we have 3 dedicated floors for our research group. This is the first floor. This is where we have our discussions and meetings. This was taken when we had a discussion with the industry for IoT project, I believe. And this is not even a quarter of our members. And then we also have dedicated, so I'm going to give you a tour of our lab. So this is our tapered fiber fabrication area and our sensing area. The first picture on your left is where we conduct our gas sensing experiments. We do it in the hood. As you can see, there's 3 lines connected to the hood where it supplies the gas. And the middle part of this figure is the Vitron machine, which is the machine that we use to fabricate our tapered fibers. As you can see on the monitor is a diagram of the tapered fiber, and actually you can input the parameters of the tapered fiber that you want. So the machine does it for us with the help of our technician, Mr. Zamili. And on your right is where we conduct our experiments that is related to tapered optical fibers, sensing experiments that is not related to gas. So if we don't have to use gas, we don't use the hood. So we just do it in the common area. All right, so we also have a dedicated area for our materials processing. Our latest gadget is the rotary evaporator. It's our new gadget. And the middle part is our vacuum oven. We also have equipment for sonication, liquid phase exfoliation. I'm going to tell you more about that later. This is our dedicated area for our fiber laser experiments, our SPR experiments, and also our optical communication simulation. We have PCs dedicated for simulation. We use VPI photonics for that. That is under Dr. Zuraida. If you are interested to do simulation, you can contact her. And this looks a little bit messy, but you know how students are. All right, you are more than welcome to visit us when PKP is over. You are more than welcome to collaborate with us or join us. And again, our expertise are in sensors technology, photonics engineering, materials engineering, and also wireless communication engineering. Okay, so that was an introduction. So let's get into our topic. So before we dive into passively pulsed fiber lasers, I'm going to talk about fiber lasers and pulsed fiber lasers so you have an idea. If this is new to you, I'm going to make it very simple. All right, so I'm going to give you a recipe about how to make a fiber laser. If you are in this field, this is going to bore you, but this is a crucial part that is often overlooked by students, is the recipe to make a fiber laser. There's 3 key ingredients to making your own fiber laser. Is that you need to have an active fiber. What is an active fiber? It is basically an optical fiber where it is doped with rare earth elements, and the rare earth elements are erbium, thulium, ytterbium, and you can choose the rare earth elements that you want depending on the emission of your laser. So it is important to choose the correct one so that you know what you're getting, right? So that is your first key ingredient to making your own fiber laser, is to have an active fiber. And this is how it looks like. A spool or optical fiber, it just looks like that. All right, so your second one is the optical pump. Now the optical pump looks like this. Oops, sorry. No, it does not look like that. This is just a schematic. So when you give an optical pump you give light energy to your optical fiber, what happens is that the atoms take this light, absorbs it. Okay, so I'm going to give you a schematic of that. The atoms in your optical fiber absorbs this light energy. The electrons get excited, and it goes to the excited state. And of course, it can't stay there very long because the lifetime is short. It has to go down to the metastable state so that it can stay there very long. When it is there, it's just hanging out there, comes a random light. Well, not exactly random, but it's from a spontaneous emission. This spontaneous emission triggers the electrons to go back to its ground state, and in the process, it will release a similar light that has the same frequency as the light that triggered it before. Now, something to note of, when the frequency of the optical pump will always be higher than the frequency that the electrons are emitting. So when you supply something that is higher frequency, you will get something that is lower frequency. Because why? Because it is dependent on the difference in energy level between the metastable state and the ground state. So you always get something smaller. All right. So now that we have our optical pump, the atoms are absorbing it, it's releasing it, absorbing it, and releasing it. So what happens? Is this enough to make our laser? Not really. It's a little bit low. It's not enough. In fact, it's not even enough to overcome the intracavity losses. So what do I do to make this greater? How do I amplify this light so that it can become a laser, right? Because laser is high intensity light. It's an amplified light. So this is not enough. What should I do? Do I increase the number of atoms or what? If I increase the number of atoms, this means that I have to use a longer fiber. Do I really want to do that? I could, but I don't necessarily want a longer fiber. So what can I do about this? I can put in feedback. The third key ingredient to making your own fiber laser is having feedback. And a feedback can be obtained by placing mirrors at the end of your optical fiber. Now, it doesn't look like the mirror that you use in your bedroom. It looks like an optical fiber on your right. It's called a fiber Bragg grating. You can also use a broadband mirror, but of course, it still looks like an optical fiber. So everything is in the optical fiber, even your mirrors. So when you have this optical feedback, when your atoms release when your electrons release the emission, it gets to bounce back and forth, right? It hits the mirror, it bounces. It hits the other mirror, it bounces. So this process happens over and over again until an oscillation occurs in the optical fiber. The light oscillates over and over again in this optical fiber. It requires the gain over and over again until it becomes sufficiently large and it becomes amplified light. So when this light is amplified sufficiently, it can become a laser. Right, so you have an emission. What do you do with this laser? Laser. What do you do with this laser? You play with your cat, right? Of course, you can make your own fiber laser, but typically the ones that we do in the lab is high powered, so don't use it with your cat. But it is an application. It's a legit application. All right. So, so we talked about the 3 key ingredients to making your own fiber laser. we can actually determine the frequencies in your optical fiber by this equation. It's a very common equation for laser people. So it's F equals to N C over 2L, where N is the number of modes, C is the speed of light, and you have 2L. L is the length of your optical fiber or your resonator. Because your optical fiber is resonating light, it is also called a resonator. Now, we have all these frequencies, but do we emit all these frequencies? The answer is no, we do not emit all these frequencies. Because why? The first key ingredient that we needed for our fiber laser was to have an active gain medium, right? So, and an active gain medium, we had to choose whether we wanted to use erbium, ytterbium, or thulium. And I told you, oh, I did not tell you yet. Typically, I will use erbium because I want my emission to be at 1.5 micrometer. With that said, an active fiber will have a specific profile, and only the frequencies that overlap with this gain medium profile will be amplified, and if it is amplified, it will become your laser. This is how your laser becomes specific in wavelength. So choosing your active gain medium is very important to get the emission that you want. All right. Okay, did I miss anything? Okay, I think I'm good. All right, so that is your laser. Okay, so far we have talked about constructing your own fiber laser. You needed the gain medium, you needed the optical pump, and you needed the feedback. Everything was fiber coupled, right? Everything was done in the optical fiber itself. How do you get this? How do you get everything in the fiber? You use splicing. So everything is fiber coupled. You don't need to align it because you just need to splice it. And passive cooling is possible for a fiber laser system because of its high surface ratio to volume, which means that heat dissipation is also efficient. This makes it very resistant to thermal impacts, vibration, contamination, and fiber lasers has no limitation in power. As we are speaking, there are people out there doing research trying to increase the power of lasers. So there is no limitation yet, at least. And the best beam quality, we have the best beam quality compared to other lasers. It has a high overall efficiency, small footprint. Because it is very small, it is also very portable, and the cost is not much. It's low investment and maintenance cost. It used to be very expensive, now it's not so much, right? So we have talked about continuous wave fiber laser. So if continuous wave fiber laser is so great, it emits laser continuously, there is no break in time, and it's pretty easy to make it, right? So why do we want this pulse fiber laser? What is a pulse fiber laser, and what is the motivation to have a pulse fiber laser? Okay, so a pulse fiber laser is a laser that is not continuous. Okay, that's easy, right? So it's not continuous. It means that there is a break in time in the emission. If the laser that we talked about earlier, it emits the laser light continuously, and the only way to switch it off is by turning it off. Switching it off lah, kena matikan. You have to switch it off lah. Okay, so pulse fiber laser, there's a break in time that you don't have to keep on flicking the switch. There's no switch to flick. It breaks in time automatically, right? And the optical power is emitted in short durations. It can be nanosecond, picosecond, femtosecond, and even attosecond. I would say that the current research is in femtosecond. Attosecond is rarely reported. Right now, everything is in femtosecond. All right, so let's talk about the motivation behind having a pulse fiber laser. Why is it so important, right? Okay, so let's take a look at this graph. It's a laser intensity graph versus time. Oh, do I have any questions? Okay, good. Can I continue?
I think you can continue. Mr. Mahmoud, do you have any questions, Mr. Mahmoud? Mungkin dia pun tak sedar kot.
Oh, okay.
Let me mute.
The audio.
I can mute him. Okay, Nat, continue.
All right. Okay, so what's the motivation behind having a pulse fiber laser? Okay, so let's take a look at this diagram. I mean, this graph is the laser intensity versus time graph, right? So this green box is your laser energy. It has a certain laser intensity. The laser intensity is marked at 1/4. It emits over a certain time duration, right? What happens if I use this same energy and I compress it? And I compress it over a shorter duration of time. What happens? So let's see. With the same energy, with the constant energy, I compress it. Now my laser intensity is amplified, right? I use the same energy, I compress it, it becomes higher. So what's great about controlling the pulse duration is that I get to play with the laser intensity. I get to vary the laser intensity. And what is great about having a laser intensity that can be varied, I get to control its penetration depth. I also get to control the temperature at the surface. So here is another graph that is temperature versus penetration depth indicated by Z. So here the green the green line indicates the behavior of the green laser on the top, and the red line for the red. All right, so the green laser has a temperature of 1/2 and the penetration depth reaches up to 3. Even though the laser intensity was not as high as red, the penetration depth could go further. Whereas for the laser intensity that was at 1, the temperature was at 1. It's very high temperature because of the laser intensity. However, the penetration depth is not as far as the green laser, right? So here, when we can control the pulse duration, we can not only control the laser intensity, we can also control the penetration depth. And we can also know what is the temperature. So it is very important to know what temperature it is, because sometimes material has low threshold damage and we don't want to damage our materials, right? All right, so let's take a look on the applications when we can control our laser. When we can control our laser, marking is possible, welding is possible, engraving, drilling, cutting, ablation, cleaning. So let's take a look at a video on one of the applications, a few of the applications in fact, of pulse fiber laser. All right, pulse laser. So this is an application using pulse laser for marking or engraving. So it works very fast and is very precise, right? So the next one is it can also be used for laser drilling. So this is especially important for manufacturing, for car industries, for machine-making machines, right? So that's weird. Okay, next one, laser sintering. What is laser sintering? This is not commonly known. Laser sintering is basically, I'm going to explain it first. It's basically you fire a pulse laser onto a bed of powder metal, and the the laser intensity melts the powder metal, and it welds it together, it melts it and welds it together to form a component. It's like 3D printing, but using powder metal. Previously, this was only available using continuous wave, but pulse laser has it also now. Okay, so that was laser drilling, laser engraving, and also laser sintering. All right, so pulse laser is also used in the medical field to treat glaucoma. It's used in surgeries, and it is also used in dentistry for laser bacterial reduction, in cosmetics. It is used to make your skin look better, for skin resurfacing, and also to treat skin issues, right? And in research, we use it for laser breakdown spectroscopy, also known as LIBS. You use the pulse laser, shoot a sample, the sample is heat up, releases the plasma emits a certain wavelength, and this wavelength is picked up by your spectroscopy, and you know what are the elements in your sample. So that's for research. And ultra-fast laser is also used in the imaging, is used for imaging. And this is a recent publication in 2020. They have achieved 70 trillion frames per second. So that's pretty cool. Okay, so now we talked about the applications. Let's get to know about pulse laser. So in comparison to continuous wave laser, so the continuous wave laser, we know that it emits continuously over time. It has a certain power, whereas for pulse laser, it breaks in time. So how does that look like? It looks like this. So this is the energy. So it has a high intensity compared to continuous wave, has a high peak power. The time is shorter, there's a break in time. So the difference the pulse distance is indicated by T, it is in time, and the 1 over pulse distance gives you the repetition rate. If they tell you the repetition rate is blah blah blah, so you know what it means. It just means 1 over T, which is the pulse distance, right? And the integration of this curve gives you the pulse energy, because this is a power versus time graph. Integrating it with respect to time will give you energy. And 3 dB from the peak will give you the pulse duration. So that's just a little bit an intro on the characteristics of pulse laser. What are the benefits of pulse? You get to scale your peak power. As I mentioned before, you can compress your pulse to get a high intensity and so on. Peak power scalability is possible in orders of magnitude. You can go as high as you want, as low as you want. With that, you get to control your penetration. But the disadvantage to this is the high temperature, possible deformation can happen. That is why it is always important to know what material you are working with. And another disadvantage, which I don't consider a disadvantage, but okay lah, disadvantage lah juga. It requires an extra component, right? So we will talk about this extra component in a bit. Okay, so we talked about continuous wave fiber laser in depth just now, not really in depth, the basics of it. And we want to distinguish it between, I want to distinguish pulse fiber laser with CW laser. Okay, so pulse fiber laser requires the extra component called a modulator. So what is a modulator? A modulator is basically like a switch. It turns on and off, on and off, on and off, right? So what is an analogy that can describe these two lasers in more, how does it, analogy helps us to relate better, right? So I'm going to give you this analogy. So this is a common analogy to describe continuous wave laser versus pulse. So for a continuous wave laser, you have a pipe, you have a tap that is dripping water inside a bucket. This bucket has a hole. So as you are dripping the water also flows, right? So it's not holding anything. So this is the same as electrons are continuously excited and de-excited. Whereas for pulse laser, you have a bucket, but this bucket is closed. The water drips, the bucket holds this water until the water reaches a maximum level. And when it does reach a maximum level, the cork that closes the hole opens and the water flows out freely. What this means is that when the electrons are excited, they are kept there for a while to induce the population inversion. They are kept there when it is sufficiently high, when I will talk about this principle later. When a certain condition is met, the electrons go back to the ground state and all of the energy are released together, which synchronizes all the light. Synchronization of the phases of the light, which means that the light emits at the same time, all right? So the modulator does this, it switches on and off and on and off. When it is switched off, it holds the water. When it is switched on, it lets the water to pass through. It lets the light to pass through, okay? So what makes a pulse fiber laser behave, coined as passively pulse fiber laser? Okay, because passively is something that is, when people hear, when someone who is not in the field hear about passively pulse fiber laser, what is that, right? They know what is pulse fiber laser, but they don't know what is passively pulse fiber laser. Well, it's actually very simple. Pulse fiber laser is just when you employ a saturable absorber as your modulator. Of course, modulators, there's a lot of modulators out there. There's a lot of types. SA is one of them. Saturable absorbers is one of them. And when your pulse fiber laser uses an SA or a saturable absorber, your pulse fiber laser is coined as passively pulse fiber laser. Why? Because saturable absorber works automatically. It works passively. There's no switch to trigger. You don't have to do anything. It works automatically. So when it works automatically, it works passively. So that is why it's called passively pulsed fiber laser. Okay, so for this talk, I told you I'm going to specifically talk about nanomaterials as SA. So SA based on 2D nanomaterials work based on the principle of polyblocking. Okay, so it works automatically. How does it work automatically? It works based on the polyblocking. When the light intensity is small, the nanomaterial does not let this incident light to pass through. This is to put it simply. And when the light intensity is high enough, the nanomaterials behave as if it is transparent. It lets everything pass through. This means that low intensity light will be blocked, whereas high intensity light will be passed through. When you have low intensity light, the SA behaves in low transmission mode, which means that it works as high optical loss. When your laser light is high enough, it lets it go through. It works in high transmission. It works in high transmission and low optical loss. All right, so this is called polyblocking. This is to put it simply. Of course, you can read more on it later. Okay, so the property of your nanomaterial or the property of your SA in combination with your design of your fiber laser will determine your pulse shape, your stability, and duration. So it is equally important to design your fiber laser as well as choosing the right SA, right? So there are three things to consider when you are constructing your nanomaterial-based microfiber SA. The first one is knowing your nanomaterial. The second one is to know what is your structure of your nanomaterial. The third one is to know what is the design of your microfiber. The microfiber is sometimes also called as substrate, right? So we need to know what is the design. Okay, I'm a little bit tired, so let's watch a video. Okay, so this is our technician preparing our tapered fiber. So he removes the coating, cleans it with alcohol, puts it on the stage, heats it up, pulls it apart. When it pulls it apart, it makes the optical fiber thin. Okay, so it's heating it up. That glowy thing is actually high temperature. Puts it on the stage, heats it up, pulls it apart. Okay, I never get tired looking at this video. I like it. Okay, so that is how we prepare our tapered fiber. Of course, you can do this manually. You don't have to have a machine. You can do this manually using the heat and pull method. Use a flame, pull it apart. Of course, there's a certain technique, there's a certain skill in doing that. So please berguru dengan orang yang bertauliah. Alright, so tapered fiber can be prepared using the heat and pull method. Under the microscope, it looks like that. Okay, so the parameters that we usually have to input in our machine is A and C, the transition region. The transition region is the region where it transitions from the optical fiber to the waste region, to the thinnest part of the optical fiber. The waste region is the thinnest part of the optical fiber, denoted as region B. And you have G as your waste diameter. So these are the parameters that we usually choose for our tapered optical fiber. And choosing the right tapering angle will determine whether your tapered optical fiber will have a large coupling or small coupling of the fundamental mode with the higher order mode. So about this, Dr. Yasmin will explain more. She will have another talk on this, I believe, in one month's time. All right. So why is it important to know the design of your microfiber before you use it as an SA? Because when you make your waste region smaller, you get more fringes. Do we want this for our SA? I'm not sure. We haven't tried with the fringes one yet, but the ones that we have used with our SA, for our SA, is between the spectral profile of 1.2 and the spectral profile of 8 micrometer. The parameters are not exactly that, but the spectral profile should look around like that. It's between being flat to having mild fringes, all right? So we typically choose tapered fiber that has that kind of profile, and it is called adiabatic tapered optical fiber. Okay, so that is the design. So what is great about using tapered optical fiber is that you get to deposit your nanomaterial at the waist region, and when light propagates into your tapered optical fiber, an evanescent field is formed, and this light interacts with your nanomaterial, and this is where your assay happens, right? The light matter interaction is very important in this case. So the benefits of using tapered fiber is that it is easy because we use a machine. It is also easy if you want to fabricate yourself. Low cost fabrication, yes, it has a large and strong evanescent field. It has a tight optical confinement. This depends on the design of your tapered optical fiber. It has a long non-linear length for light matter interaction. This is very important. We have seen cases where SA made out of thin films and using fiber connectors suffer from low damage threshold. It can't be operated at high temperatures or high powers. So having a long non-linear length is especially important, and also because it is made out of optical fiber, it is easily coupled to other optical components, making our system an all-fiber system.
Sorry, I think we lost connection. Let me contact Nadiah first.
The top part of that fiber, exposing the core. And this part of the exposed core is where you deposit your nanomaterial. It exposes the fiber core. The fiber becomes asymmetrical. Is that bad? I don't know. Maybe. So this is how a D-shaped fiber looks like. You deposit your nanomaterial on the grinded part of the fiber, and your evanescent field forms there. Because evanescent field has to escape the light. The light has to escape the fiber for evanescent field to form. So you only have the top part to work with as your SA, right? So the device becomes polarization sensitive because it is not symmetrical. Switching between mode lock and Q switch is possible by tuning the PC. It is easily done. I'm not saying that tapered fiber can't do that, but for D-shaped fiber, it is more easy to do it. Non-symmetrical geometry induces polarization independent losses. Sometimes this is good, sometimes this is not, depending on your application. Hybrid mode locking is also possible, which utilizes slow and fast absorption. Okay, but that's for another time. Long non-linear length, and also easily coupled because it is also made out of optical fiber. All right. Okay, so we talked about our microfiber. Now it's time to talk about how to process our nanomaterial, right? So we have two types of fabrication method. We have the top-down, and the bottom-up. The top-down basically means that you are thinning it out from bulk, and bottom-up is basically you are trying to grow your material. So I'm going to cover a little bit on that, top-down and one from bottom-up. So the first one is mechanical exfoliation, my favorite because it's easy. It's called the Scotch tape technique. This technique won the Nobel Prize in 2010 and got everyone crazy about graphene because they discovered, oh, graphene can be exfoliated just by Scotch tape. So that was, I would say discovery was kind of crazy because they use a Scotch tape, right? And what they do is that they use the normal force to peel off the layers. They peel off, keep on doing that until they got a single layer graphene. And they deposited that graphene on a fiber connector, connected it together, it became an SA. So it was like a breakthrough moment, right? So this type of technique provides the purest 2D materials with less defects compared to others, produces high quality single crystal flakes, However, because you have to, it's very labor intensive, it's not scalable technique. It's either you have to have a wide task force to just do it, right? Very labor intensive, so not suitable for industries. So that's a figure of that guy peeling off layer by layer, and in the end he got the single layer graphene. Hurrah. So next one, liquid phase exfoliation. Basically using liquids to exfoliate your layers, right? So look at the diagram here in A. So the author he put in graphene flakes into IPA, isopropanol alcohol, sonicated the graphene flakes in the alcohol, and what happens? The graphene flakes was exfoliated, became thinner, and also the size was also reduced. It became smaller. What's the great thing about LPE? It is very scalable. You can do this with a lot of amount at one time. You can do it a lot. You can process a lot of material at one go, basically. So however, the downside to this is the prepared nanosheets are random. You can't exactly control it. Sometimes you get mono, sometimes you get a few layer flakes. It can be carried under ambient conditions, so that's great. And another technique that can be combined with LPE is using ultracentrifugation to help sort out the material flakes by thickness, because again, what you get is random. The author in here also added PDMS to his graphene flakes to make a nanocomposite. He stirred it on a hot plate with a magnetic stirring bar and then added a curing agent. What was that? Okay, so adding the nanomaterial to make a nanocomposite is great because it protects the nanomaterial from degradation. This is especially important if you want to extend the shelf life of your SA, right? And then it also secures optimum contact with the fiber. When you deposit a cured nanocomposite, basically it won't go anywhere unless you try to peel it off. So it's very secure. Protects your nanomaterial from degradation, so it's excellent. Next one is dip coating and optical deposition. Dip coating is typically used with optical deposition. Dip coating is what it means. Just dip it into a solution of nanomaterials. You inject light, and the light that propagates in the optical fiber interacts with the nanomaterial in the solution, and the nanomaterial sticks onto your fiber. When you do not use dip coating with optical deposition, your solution, the solution that you dip in, must be viscous enough so that it grips onto the tapered fiber. This is what the author did. He dipped it into a composite. A composite is made out of polymer, so it has a certain viscosity, and that is great. And then he dried it on a groove, right? And because of gravity, some of the composite gathers on the side, as you can see in the diagram here in A. It gathers on the side. But you can see on the top part, there is an even coating and the SA is done. So it's pretty simple. And then the last one is bottom up, CVD, chemical vapor deposition. I'm not an expert on this technique, but it guarantees a high quality crystal lattice and uniform thickness because you really can control what you're getting. It requires a lot of preparation. The growth rate is very, very slow unless you seed it to make it enhance, to make the growth enhance. And of course, that requires more preparation. And I believe chemical majors will love this, right? You're playing with chemicals, right? And CVD is you can do it. It's a scalable technique because you can do it you can mass produce it, but requires a lot of preparation. The only downside is the preparation part. Okay, so we talked about how to process the nanomaterials. So let's talk about the nanomaterials. So what type of nanomaterial should you use for your SA? First of all, it should have a strong non-linearity. Not all materials can be used as an SA. It has to have a strong non-linearity. It should offer relatively low cost because the ones that we have now is cheap. So if you're going to use a material that is expensive, it would beat the purpose, right? We always want to go cheaper. We always want to go simpler. It should also have a fast response time. You should know what is the band gap energy. so that you know what is the absorption wavelength. It should have low optical loss. It should be able to handle high power. It should consume less power, ease of fabrication and integration, as I mentioned before. Okay, so band gap energy, if you don't know, it is the difference of energy between the valence and the conduction band. This is where you determine what is the absorption of your material. Okay, so the first one, graphene, has zero band gap. That is how it looks like. That's a direct cone. Okay, so having a zero band gap means that it is wavelength independent, which means that it can operate at any wavelength that you want. An author reported, I don't remember who's the author, but they reported an assay made from graphene, which was able to mode lock C band and also L band using the same SA. They had two cavities and the common point was the SA, which was impressive. You could mode lock two bands together, making a dual band fiber laser. Okay, so graphene, as I mentioned before, it can be peeled off using the mechanical exfoliation. It is also used with, it is also processed with LPE, liquid phase exfoliation, because of its weak interlayer van der Waals forces. So between the layers, it's not very strong. So that is how LPE and mechanical exfoliation is excellent to peel it off. Most people, no, not most people. One of the misconceptions is that using a single layer graphene is sufficient to get mode lock. But that's not always the case. Typically, people will use several layers of graphene because graphene on its own, as a single layer, has low modulation depth. You want a certain modulation depth before, you want a high modulation depth to get your pulse laser. Okay, so the diagram on the bottom here shows the graphene deposited on the microfiber. So it's not very interesting, but that is how it looks like. Okay, so graphene is popularly used with fiber connectors as SA. And I told you before, fiber connectors are not really great because they can't tolerate high power. Okay, then we have TMDC, transition metal dichalcogenides. Everything is hard to pronounce. It has a tunable band gap of 1 to 3 EV. Okay, so you can actually tune the band gap of TMDC, which is great. You can make it do what you want, right? So band gap engineering, you can do this by reducing the number of layers or introducing defects, right? Here, molybdenum disulfide, initially in the bulk form, it was 1.29. When they reduced the layers, it became 1.8. And then when they introduced defects, it became 0.8 EV, so even smaller. So one of the defect that is commonly reported for transition metal dichalcogenides, I'm just going to call it TMDC because it's very mouthful, is edge state defect. What is edge state defect? It's hard to explain what it is, but it produces subband in the band gap, subband gap in the band gap. So you have subbands in the band gap. So that is how they tune the band gap. That is how they control the band gap to be what they want it to be. So edge state that generates subband gap within the band gap shows broadband SAs. The current longest effective wavelength demonstrated with TMDC is 2 micrometer from the band gap engineering. Right? So TMDC is very versatile. And then we also have black phosphorus. Yes, it is black. It possesses a thickness-dependent direct band gap, which means that the thinner you go, you get a different band gap. Band gap is widely tunable from 0.3 to 2 EV. So just now, graphene had 0 band gap. TMDC was 1 to 3. So black phosphorus is in the middle. It's 0.3 to 2. It slightly overlaps with TMDC, closer to graphene. It has strong light matter interaction, important for SA, possesses high carrier mobility. However, it has poor stability and easily oxidizes. So maybe black phosphorus has to be combined with composite, right? Has to be combined with polymer to make composite. Similar to graphene, the different layers are stacked together via weak van der Waals forces, which means that liquid phase exfoliation, mechanical exfoliation is excellent to exfoliate black phosphorus. So the reported saturable absorption spans from 400 to 2 micrometer. That's great. It means that the band gap tuning was achieved. Okay, and the fourth one is transition metal oxide, or TMO. The band gap is tuned by controlling the particle size, thickness, and the morphology of the sample. It has enhanced nonlinear optical absorption. It has a wide absorption band. It has an ultra-fast response time, has a high damage threshold, good mechanical strength, high resistance to photocorrosion, high thermal and chemical stability. Transition metal oxides has been widely used for other applications, but as an SA, it's not that explored yet. So these properties make it have good durability and shelf life. The band gap tuning of TMO is not conclusive yet because there are other TMOs that has not been explored yet. So we are still waiting on that. Or if you don't want to wait, you do the research. And other nanomaterials include topological insulators, where it has a graphene surface state. It has zero band gap at the surface, and it has a semiconductor or insulating property in the bulk. And then you have bismuthine, which is layer-dependent band gap from 0 to 0.55, and antimonine band gap variation via strain, which is something very interesting. So what are my thoughts about this topic, right? What's in the future? The exploration of novel assays is still a long-standing goal. We have a lot of materials that has not yet been explored. And scientists have predicted that we can get novel materials by stacking these different nanomaterials on top of each other like Legos to get a new material. So we should also look into that direction for our SAs. So I think with that, I would like to end my sharing, and thank you very much for listening. That is all. Pew.
Thank you very much, Nat. Thank you very much for the very thorough and detailed sharing. Very impressive, comprehensive. Starting from the physics part of it, I feel like attending a physics class. Okay, any question from the audience? We have many people here, around 40 people. Any question you can put your audio and ask. You can also post your question on the chat box. I read your question.
Can we have Dr. Nadiah's slides? Yes, but I need to sort out my references first. Can I do that? Okay. All right. Thank you. Any questions?
If no question, I would like to ask you one question. What is the peak power of the fabricated laser?
Peak power of fabricated laser. Which laser? The continuous wave or the pulse? From what material? How was the band gap and band gap within band gap being measured? Peak power must be pulse. Okay.
No. Do you understand the question? The first one from Fariza. Fariza asked, what is the peak power of the fabricated laser?
Peak power of fabricated laser. Oh, pulse laser. Okay, so pulse laser, the range can go up to 100 kilowatt. The ones that I've read. So it can go hundreds of kilowatt peak power. What is the peak power of fabricated laser? Very informative. From what material? From what material? I'm not sure. I need to get back to you on that one. How is the band gap being measured? We have the characterizations for before we use it as an SA. We actually have to characterize it. And this is the part that I did not touch on this sharing. We for the appearance of the material, we use FISAM. For the elements of the fabricated material, prepared material, we use EDX and also XRD. And for the band gap, how do we calculate this? I forgot the. I think it was UV-Vis, and we use a torque plot to figure out the band gap. But it is on Wikipedia, I'm sure. Okay. Is there any other questions? In case of the pulse laser collapse due to damaged threshold of threshold, it can be regenerated again. So when once your material reaches the threshold damage, it can no longer be used. You have to fabricate a new SA, but only the SA is damaged. The fiber laser will be fine. How can we control the gap of TMDC while using mechanical exfoliation technique? How to mechanical exfoliation? Okay, so I told you with mechanical exfoliation you can actually control the number of layers, right? With each thickness you have to characterize it for its band gap. So that is how you get to know what is your band gap actually. What happens for when laser enters inside optical modulation? For what type of? What happens for laser when entering inside optical modulation? What type of laser? Okay, so the modulator that I talked about was I just explained it very in basic terms. So a modulator acts like a switch, right? So there are many types of modulator, such as NPR, such as real SA, such as SESAM, SESAMs. So the one that we are using is SA, which works automatically, right? It blocks the light when it is not high enough, and it lets the light to pass through when it is sufficiently high. So that is, so if I would want to answer what happens inside the material, I do not know. Okay, so that's the physics part of it. I will need to read on it. Okay, thank you very much for that. Thank you, you're welcome. I don't know what happens inside. I really don't.
Dr. Nadiah.
Yes.
Yeah, okay, Akmal here. So I would like to ask that just now, I mean, in the earlier of your presentation, you mentioned that your team, I mean, your WebNet team, going to integrate with the IoT. Is it correct?
Yes.
Right. So, is there any plan for your project to integrate with this IoT?
So far, not yet. We are currently integrating IoT with electronic sensors for now.
Oh, all right. So maybe later you can like
Yeah, maybe in the future, inshallah.
develop something that can trigger this fiber laser, using remotely. Maybe.
Mm-mm.
All right. Thank you. Good job.
All right, thank you so much.
Okay, any other question? Right. If no, before you guys leave, can we have one photo session? If possible, if you can turn on your camera so that I can take a snapshot. Is it okay? Nampak ramai kat sini. Dr. Hafiz. Prof Azir, apa khabar Prof? Can you turn on your camera? Apa khabar Prof? Work from home ke?
Alhamdulillah.
Okay.
Ini dah gambarnya.
No, Prof, tak ada pun.
Belum
Tak ada
lagi.
Prof. Turn on camera lah Prof.
Mana Prof?
Dia ni
Dr. Hanif tak ada ya? Dr. Hanif?
Data Hanif tak ada. Nat,
Yep.
Nat, stop
Stop sharing.
presenting.
Okay.
Stop presenting sebab tak nak bagi nampak slide. Okay, thank you Nat. Thank you very much Nat for your sharing.
Thank you for joining.
Okay, before that, let me count by 3. Nampak dah muka Prof. Kat office ke Prof?
Kerja.
Okay, smile. 1, 2, 3. Okay.
All right. I'll see you around, everyone. Bye-bye.
Alright then.
Okay, thank you everyone.
Yeah,
See you.
okay, thanks everyone.
Bye. InsyaAllah jumpa
Bye.
lagi in the next, maybe in the next Photonic lecture series. Thank you for joining us. Thank you very much, Nat, for your sharing.
Okay,
Okay,
bye.
take care. Be safe. Bye-bye.